Okay, so hi everyone. Today we will start our class for week 4. Okay, so before starting our class for today's topic, let me just discuss briefly about the things that we discussed in the last class. So last class we mostly discussed about transport phenomena. So we started our discussion with three types of equilibrium. One is the thermal equilibrium. Second one was the chemical equilibrium. And third one is the mechanical equilibrium. Okay, now so yeah, so these are the basically three types of equilibrium. So the origin of the thermal equilibrium is the temperature gradient, right? So if in a system there is a temperature gradient arises, this basically causes the heat to transport from higher temperature to lower temperature region, right? So because of that, because of this temperature gradient, basically there is a transportation of heat is occurring. Okay, so that's why the temperature gradient basically disrupts the thermal equilibrium, and because of that disruption, this transport phenomena of heat can occur. Okay, and we have discussed that. Uh, so for 1 second, yeah. So for thermal gradient, so if the thermal gradient occurs, so the heat that is basically transported because of the gradient is basically written by this relation, which is the Fourier law of heat transportation, K into dA to dt dz. So this is basically the temperature gradient. Okay, next is the uh, next was the chemical equilibrium. Okay, so chemical equilibrium happens if there is a concentration gradient arise into the system. Okay, so if there, let's suppose there is a concentration gradient, so in a gas assembly or in a room, let's say one part of the room has, let's say, higher gas density, and one part of the room has the lower gas density. So similarly the gas tries to redistribute itself in a homogeneous way. So because of that, the gas will move from higher dense region to lower dense region, right? So because of that, there is the gas basically moves, and this basically creates the thing that is known as diffusion. Okay, so basically this concentration gradient similar way disrupts the chemical equilibrium, and because of that this transportation of gas molecules occurs. Okay, and here this the flux of the gas molecule or fluid molecule, whatever it is, that flux is basically denoted by J, and that is related to the concentration gradient via this equation, J equal to minus D dA. dA is basically a small area, okay, into dN dz. Okay, so dN dz is basically the concentration gradient. Okay, and third one is the uh, mechanical equilibrium. Okay, so mechanical equilibrium basically happens like uh, because of velocity gradient. Okay, so like let's suppose velocity gradient. Okay, so let's suppose in a gas or in a fluid, uh, there are multiple layers of fluid like this. So let's suppose one layer moves faster than the layer right beside, right like below of it. In that case, there should be a friction that would occur between these two layers, right? So because of that, the both the layers tries to like moves with the equal speed, and because of that there is a friction that is basically creates between those two layers, which we know as viscosity in the system. So this velocity gradient basically creates this viscosity into the system, and this force that is acting between these fluid layers is basically given by this Newton's law of viscosity, where F is equal to basically minus eta dA du dz. So du dz is basically, or dv dz, it's basically the velocity gradient. That means if you like move, let's suppose this z axis, if you move along this z axis, what is the velocity, how the velocity basically changes along the z axis, so that quantity basically calculated by dv dz. Okay, so eta is the viscosity coefficient of viscosity. Okay, yeah. So these are basically three types of transport phenomena we have discussed last class, and also we have discussed like from using a general treatment. Okay, like if there are two layers, if there is some physical quantity, but it can be heat, it can be concentration, it can be velocity, whatever it is. If the two layers are like separated by a certain distance, let's suppose that is dz or L, sorry, that was L. In that case, let's suppose one layer has some physical quantity H, other layer has some physical quantity H plus L into dH dz. In that case, we have discussed like we have also first proved that what is the minimum maximum value of L that can the system can attain. We know that L, the molecule should not suffer any collision from moving from this layer to this layer, right? So so in order to consider that fact, the maximum value of L that can achieve is 2 3 lambda. Okay, so lambda we know is the mean free path here. Okay, lambda is the mean free path, that we have also shown how this calculation and all is coming. And for different cases we have calculated, like suppose if what is this, so let's suppose h is some velocity gradient. Okay, let's suppose there is some momentum gradient arises, and because of that this h quantity is basically given by the momentum m, let's suppose vy, something like that. In that case we can calculate the viscosity coefficient. Okay, so that viscosity coefficient basically given by this m eta equal to m c bar into 3 by root 2 pi d square. D square is basically diameter of the molecule. Okay, so similarly if h suppose is now, so first we consider it as a momentum. If you consider h as a heat, uh, heat as a physical quantity here, so in that case h would be equal to cvm into t, that is a specific heat. In that case we have calculated the this heat capacity. Okay, so that is basically not heat capacity, this what is this called, heat conduction coefficient. Okay, this k kappa thing. Okay, coefficient of heat conduction. Okay, so this kappa is basically given by 1 by 3 lambda c bar, sorry, n c bar cvm. Okay. Similarly, if h is something like molecular, if h is molecular gradient, so quantity, what are, somehow disconnected. Just wait a minute. Okay. Can you able to hear my sound?
Yes, yes.
Okay, okay, just a second, something happened here. I'm not able to join. Just a second. Okay, so okay, so similar way for if h is n, then in that case we have calculated its we calculated the diffusion coefficient that if h is n, so in that case the physical quantity is the concentration. In that case we have calculated the diffusion coefficient. So that is basically given by d equal to 1 by 3 c bar lambda. Okay. Now, and lastly we have discussed about the molecular effusion, right? So molecular effusion is like if there is a small hole, very small hole, if the diameter of the hole is very much smaller than the mean free path of the molecules, in that case the number of molecule that would be come out from this hole, that particular quantity is given by dn. If a is the, if a is the a is the dA is area is a is the cross section area, in that case the number of molecules that would be escaping from this small hole into the time dt is basically given by dn into minus phi a dt. Now similarly, so from here you can write it as dn dt equal to minus phi a. Okay, now you can write it in different way. Okay, so last class there is a question, so you can write it in terms of m also, so like, and write, so if let's suppose m is the mass of one molecule. Okay, mass of one molecule. In that case, the total mass you can write m equal to m into n. Okay, so this is the total mass of the gas. Okay, let's suppose n numbers of gas molecules are there. In that case, you can write it like, write this equation as dm equal to, sorry, dm equal to dt equal to m into dn dt, right? So you can write dn dt equal to dm dt by 1 by m. Now just substitute this thing here, so this will give you dm dt equal to minus m phi a. Similarly, in terms of volume also, okay, let's suppose now you want to write in terms of volume. So in that case, you need basically the number density. Okay, here you need the mass of one molecule. This is the capital M, okay, and this is small m. The small m is mass of one molecule and capital M is the mass of the total molecule. Okay, now now for the volume, if you write in terms of volume, then you need number density. So what is the number density? Number density is the number of molecule per unit volume, that is n by v, right? Now you can write n equal to n into v. So now you can write dn dt equal to n into dv dt. So now just substitute this thing here, right? So that will now give you n into dv dt equal to minus phi a, that is basically dv dt into minus phi a into n. Okay, so these are basically two important formula in the question. Either of these three from formula, like you have to use. Okay, this is in terms of n, this is in terms of m, and this is in terms of v. So how the number of particles change during the effusion process, maybe that can be given, or how the mass is changing inside this box, that can be given, or how the volume can change inside the box, that can be given in the problem. So depending upon that, these three equations can be used. Okay, okay, so now we are going to the today's topic. So now today's discussion is about Brownian motions. Okay, so all of us more or less know about this Brownian motion. Okay, so we know that it's first discovered by a botanist named Robert Brown. So where he basically observed some of like this kind of random motion of some particles in a fluid. Okay, so fluid means it's basically pollen extract, something like that, in a water. So there he observed although they are non-living object, but still they are showing some kind of a random motion inside of the fluid. So from that, from this experiment basically, or from this observation, this name of this phenomena is basically known as the Brownian motions. Okay, now yeah, yeah, so now, so there are several there are many characteristics exist in the Brownian motion. So these characteristics are basically very much important. So if you want to basically derive any equation of motion of the Brownian particle, or if you want to basically study any statistical property in terms of mathematics, in that case you have to always consider these features of this Brownian motion. Other than that, you basically cannot able to basically characterize any kind of statistical properties if you don't consider this features of the Brownian motions. Okay, so some features are, so the one of the most important features are these are random motions. Okay, so like uh, if there are, let's suppose, two particles which are very close vicinity, like in very close vicinity, the particles movement, like movement direction, velocity, everything is like random. So like how the particle of, let's suppose, particle 1 is moving, simply not related to how the particle 2 is moving. So basically these two particles are completely decorrelated from each other. Okay, so their motions like not uh, like uh, uh, like not affected by each other. Okay, this is like completely random motions. Okay, so there is no what you can say correlation between their motions. Okay, second is the motion is independent of any mechanical vibration of the, yeah, so independent of any mechanical vibration. So basically these are spontaneous motions. Okay, in whatever container you put those particles, these bounded particles, whether the container is vibrating or not vibrating doesn't matter at all, because these are completely, you can say, eternal kind of motion, eternal spontaneous motions. It doesn't depend on external effect. If you don't put any external effect also, you can see this spontaneous eternal Brownian motions. Okay, so these are basically eternal motions. Okay, third features is, for smaller particle size the mass is the motion would be higher. Okay, so the smaller particle face greater motion. Okay, similarly, opposite, in opposite, like if the particle size is bigger, then it will face less motion. Okay, fourth one is it's dependent upon the viscosity of the medium. Okay, so viscosity of the medium. So it's like, if suppose this is a general common sense, if you put, like if you made the viscosity too much high, if you, let's suppose this coefficient of viscosity eta, if you made it very high, then during the motion, right, if the particle tries to move, the friction force, that is friction force that is proportional to the eta, that basically acting onto the opposite direction, right? So if the eta is higher, the friction forces would be higher. So in that case, this Brownian motion will be hindered, right? So that's why if eta is higher, this so if eta is higher, so the motion would be less. So that means for less viscous basically results to higher motion. Okay, and 5 is the temperature. Okay, high temperature results to greater motion. Okay, basically these motions are somehow related to the thermal energy of the particles. Okay, that we have discussed, that is basically given by half kVt. Okay, for a single for degrees of freedom. Okay, so these motions are basically related to basically the energy of the motions are basically related by this thermal energy. So because of that, if you increase the temperature, this thermal energy inside the particles will also get increased, and because of that, the motion will become the particle will tends to show a higher Brownian motion. So these are basically very fundamental 5 characteristics, or you can say general features of this Brownian particles. Okay, So whenever you want to model these Brownian particles, you have to always keep these five properties in your mind. Okay, temperature, viscosity, the size of the particle, and the motion of the particle should be always random. Okay, yeah. So Einstein, so correlation. Okay, so yeah. Now in this experiment, like in these experiments of Brownian particles, what the people most do, that they like in a what they did is that in a fluid or in a solvent system. Okay, let's suppose in general the solvent system is basically a water system. Okay, there are many solvent molecules are there. So in that solvent system they put a Brownian particle. Okay, inorganic particle, some that kind of particle, where the characteristic size in general of these Brownian particles are higher than the water molecule. Okay, and if you put it like this, then what they observe is this. So these water molecules, they are calling it as the host molecules or the solvent molecules, host, and these particles, these external particles that we are telling it as a Brownian particle, that we are telling as guest molecule. Okay. So if you put this guest particle or molecule inside this host molecule, so basically what happened, this host molecule itself execute these random motions. Okay, so because of that, this basically, so this, as this host molecule moves, so it will collide, so collectively collide with this big guest molecules, right? And because of that, these guest molecules also shows this random motion because of the collision of this host molecule. Okay, and so, and because of that, these particles also shows random motions due to collision from host. Okay, and so what from experiments also or from simulations also, what it has been observed, that if the molecule size is bigger, okay, what happens, this collisions basically comes from different directions. Okay, like this is, let's suppose this is a external particle. If these are the small solvent particles, so if the particle of this external particle size is higher, so this, all this collision directions that comes from different direction basically averaged out. Okay, so these forces are basically balanced out. So because of that, the larger particles or this larger host particle shows less motion. Okay, shows less motion as the forces balance out. Okay, so for the case of smaller particles it is opposite, right? So it face some like inhomogeneous force, and because of that it moves, it face like it face higher motion compared to the bigger molecules or particles. Okay, now next is yeah, so this is one of the region. Okay, why we have also written here also, right? So the particle, smaller particle face greater motions. Okay, now so yeah, so one of the most important concept in this of like to study these Brownian particles, since the particles motions are random. Okay, so to characterize the motion of the particles, it is a very important quantity that in general people calculate, to basically quantify their motions. That quantity is basically known as the MSD. Okay, MSD, that is mean square displacement. Okay, mean square displacement. So what does this mean square displacement is? Okay, so first we have to define a time scale. Let's suppose a time scale that is tau. Okay, so this time scales basically depends upon like what is the size of the particle, or what is the what is the duration you, up to what duration you want to study the particle. So depending upon that, this tau or the time scale you can choose. And what you have to do, let's suppose this is a Brownian particle. So initially it has a position, let's suppose x0. Okay, and after the time interval tau, this moves, let's suppose, from x0 to x1, from x1 to x2, from x2 to x3, completely random. Okay, so if you, let's suppose how this delta x1 from 0 to 1 and delta x2, that is x1 to x2, how these two are correlated, if you want to calculate, you can see there is basically no correlation at all. Okay, these are like completely random motions. Okay, and each, like, in between each of the interval, the time interval is basically given by tau. Okay, now if you if you calculate this displacement by tagging the particle, like in an experiment or something like that, if you tag that particle, if and you can calculate the displacement, this delta x1, delta x2. Okay, delta x1, delta x2, delta x3. Okay, like this over the, like, this displacement basically the displacement that is covered during this interval, that time interval tau that we have previously defined. If you calculate all of this displacement, then from the definition itself you can calculate the MSD. So how, what is the MSD? That is the mean square displacement. So you have the calculated the displacement, then you do the square of the displacement, then delta x1 square, delta x2 square, delta x3 square, the square of every displacement. Then what you have to do, mean of it. Okay, so like, let's suppose you have done n numbers of observations, so just delta x1 square, delta x2 square plus delta xn square, you have add the average. Okay, average out. So this gives you the MSD. Okay, the mean square displacement. First you calculate the displacement, then you do the mean, then you do the then you do the square, then you do the mean. Okay, this is a very important quantity that basically we study to characterize the motion of the particle. Okay, and and basically Einstein, I guess, yeah, yeah. So Einstein first calculated, okay, this mean square displacement of Brownian particles in terms of the transportation property of the host fluid. Okay, so transportation property I've already discussed. So in this fluid, since the movement is involved, uh, so transportation property means here they are basically directing the viscosity actually. So Einstein first uh, calculated this MSD, how the MSD is related with the transport property. Okay, more specifically how with the viscosity of the host molecule. Host means the solvent molecule. Okay, so in order to derive that, what he have considered, like, he considered 1D what is this called, 1D movement of Brownian particles. Okay, so let's suppose this is a, so particle is just moving, can move along this x-axis only. Okay, not in y-axis. So what he considered a small tube where, let's suppose, here the particle that is coming is given by pi, particle that is going inside, let's suppose pi 1 from this side to this side, and particle that is coming from this side to this side, let's suppose pi 2. Okay, and the number density of particles, let's tell this point as p and this point as q. So density of the particles at point p is n1, and density of particles at point q is basically given by n2. If this is the case, if the gradient of the particle is dn dx is n2 minus n1 by r, sorry, let's suppose it's normal r. Okay, and what is the r that I have not defined? So r is basically distance between them, and and tau is basically the time that is required to travel the particle from p to q, I mean to cover the distance. Tau is the time to cover distance tau. Okay, so in that case, sorry, it's r. So in that case, number of particles that is going from this side to this guy given by pi 1 is given by basically half n1 ra. Similarly, particle that is moving from q to p, that given by pi half n2 ra. Now the so the net particles is basically pi 1 minus pi 2 n1 minus n2 by ra by 2, and from it so this is the basically the total number of particle that is moving. Okay, now from this thing you can basically calculate the flux of the particle. Okay, so flux of the particle, you have to basically uh, not to get the flux, what you have to do, flux is basically number of particles that is moving per unit area and time, right? So you have to multiply the sigma by tau into a, so this basically gives you the flux, that is n1 minus n2 by 2 tau into r. Okay, you can write, yeah, so now you can write it like this. So we have already defined like the this is the gradient basically, so we can substitute this equation here. After doing that, we can write this quantity as minus r square 2 tau dn ds. It's s, right? Yeah, dn ds. Okay, this is a small distance. Yeah, so this is the flux basically. Okay, now this is basically, yeah, sorry, I told about viscosity. It's not viscosity, it's a diffusion coefficient. Okay, the transport property, that coefficient is not viscosity coefficient, diffusion coefficient. Okay, yeah, so this basically given like this flux, we know that from what is the law, I forgot. Yes, this one, yeah, this concentration gradient. Okay, so this concentration gradient basically gives us this fixed law of diffusion, right? So this, from the fixed law of diffusion, we know J is basically minus d dn ds, right? So if you compare these two fluxes, from there you can get the diffusion constant as r squared by 2 tau. Okay, so this is the expression of diffusion constant. Okay, now now this is one way of calculating the diffusion constant, like so the particle basically moves from one place to another place. Okay, like the Brownian particle. Okay, so because of that, so that means basically the particle basically diffuse from one place to another place. So if you observe the motion of the particles, like in short time interval, you can see the particles movement is completely random, different direction. But if you observe for a longer time, you can actually see the particle move from a particular direction, particular position to a certain particular position. Okay, it's a like finite movement, you can see. Okay, this is delta r, that is in long time. Okay, but if you see in short time, you can see like random movement. Okay, so it's a way you can see the particle diffuse from one place to another place. So that diffusion constant is basically related by this relation. Okay, next is next there is another way of proving this diffusion constant, that is by using the concept of osmotic pressures. Okay, so diffusion is basically nothing, is basically is the transport, one of the transport property of the Brownian particle. Okay, so this is basically this is the expression. So if you know tau and r square, then you can, from there you can basically calculate what is the diffusion coefficient. Okay, next, from the concept of osmotic pressure also you can calculate this expression of the diffusion coefficient. Okay, so yeah, so what is the osmotic pressure? You know, like if let's suppose this is let's suppose a solution, some water, like solution means water plus some solvent. Okay, some water plus solvent. Okay, and in this area, let's suppose there is only water. No, it's solid. Water plus some particles, let's suppose. Okay, yeah. So these two so these two container, okay, let's suppose separated by some permeable membrane, thin permeable membrane. Permeable membrane means only this water can flow from this membrane, this particle cannot flow, because this basically this holes in the membranes, the size of the holes of the membranes is much smaller than the size of the particle. So because of that, the particle can only move uh, from one side to another side. Okay, so if so that means, so to in order to make the concentration in both the sides equal, so there would be some osmotic pressure that would be created on this membrane, right? And that osmotic pressure is basically given by P equal to nkt. Okay, if n is basically the number density of molecules. Okay, solvent molecules. Okay, so now from this concept you can also calculate this expression of diffusion constant. Okay, so let's suppose in a tube, the similar way, let's suppose in a tube, both the side of the tube have different osmotic pressure. Let's suppose this portion has P1 N1 kT, and this portion has P2 N2 kT. Okay, and the concentration difference similarly given by dn dx. Let's suppose this is the x direction. Dn dx is basically, let's suppose the concentration here is N2, here is N1. Dn dx is equal to N2 minus N1 by small, let's suppose it's r. Similar way, this is r. Okay, now the force. So because of this this suppose pressures are not equal. Okay, so definitely N1 and N2 are not equal. So because of this pressure difference, there would be a net force acting on the Brownian particle. Okay, so that force is basically given by F1 minus F2, where F1 is P1 into A. We know force is nothing but pressure into area, and F2 is P2A. Let's suppose this area is A1A, this area of this small tube. So in that case, if you calculate from here kBT into N1 minus N2 by A, this is the force difference. So because of this unbalanced force, the the Brownian particle will face some this particle, basically this Brownian particle where, so here these particles are there, so because of this osmotic pressure difference the particle will feel some force, right? So that force is basically given by this quantity. Okay, now for a single particle, for a particular single particle, this force is basically F by n into a. So okay, this is basically the average particle, if n is the average particle density. Okay, average particle density, this expression is the force on a single particle. Okay, on a single particle. Okay, so single particle force, basically you divide the total force by the density, like total number of particles. Okay, that total number of particles you can get by multiplying the density with the total area, right? So from there you can calculate the expression of the force. F equal to, if you substitute everything, n1 minus n2 expression from here, an expression of s and all. Sorry, this is the r. Sorry, here this is the r. Okay, yeah, that is the total volume. Yeah. So if you do all this substitution, you'll be getting F equal to minus kBT n into dn dx. Okay. Now from the Stokes law we know this, if in a fluid layer, if suppose there is some velocity difference or difference in momentum or force that's arise into the system, so because of that there is this viscous drags that acting onto the system, right? So that viscous drag force basically given by this formula from Stokes law, right? 6 pi eta rv. Okay, so this viscous drag force is only applicable if there is a spherical particle uh, moving in a fluid. Okay, so let's suppose if a spherical particle moving in a fluid with speed v, in that case with a radius r. Okay, in that case the viscous drag force that would be acting onto this particular spherical particles are given by this Stokes law of force, that is 6 pi eta, where eta is basically the viscous coefficient. Okay, now if you this, so this force and this force are basically equal. Okay, now if you just compare these two forces. Okay, so 6 pi eta rv equal to minus kbt n into dn dx. If you compare these two things, now here you can nv is nothing but a number density, so number density into the volume, so that basically gives you the particle flux. Okay, that is j, that is given by minus d into dn d. This is fixed law of diffusion. Okay, so that is the particle flux that is moving. Okay, so if you substitute this quantity here also, so after doing all of this substitution, we getting nv equal to minus kbt 6 pi eta r dn dx. Now if you do substitute this thing here, from here you will be getting minus d dn dx equal to kbt 6 pi 6 pi eta r, yeah, 6 pi eta r into dn dx. Dn dx will cancel, so the expression of the diffusion coefficient d is basically given by kbt into 6 pi eta r. Okay, this is keep in mind, this is only for spherical particle. Okay, so for the spherical particle we know how yeah. So for spherical particle we know how this basically this r, let's take it as capital R. Okay, because we are using r as this distance. Okay, so let's make this r as capital R. Okay, this is the radius, This is a different thing. Yeah, capital and smaller. Okay. Okay, now if you just substitute, if you just compare the previous two previous two expression of diffusion constant, this is the one and this is the two. If you compare this one and two expression of diffusion constant, you will be getting that. So kBt is 6 pi eta r is basically given by r square to tau, right? So from here you can write r square as kBt 3 pi eta r into tau. Okay. So this is basically a very important relation. Okay, so this is basically this r square is nothing but the mean square displacement, right? MST. Why? Because we have previously discussed, right? So r is basically the particle that moves uh, in between the time interval tau. Okay, so you have to, so in order to get the r square, so basically you can calculate over many interval tau 1, so very like many interval tau r1 square r2 square. If you average all of this, you will be getting this final r square. Okay, r1 square r2 square. If you average all of this over the interval n, then you will be getting this expression of r square. So this is basically how the particle fluctuates. Okay, like how basically the motion, so as this is a random motion, so that's why they are calling it as a fluctuation. Okay, so this and eta is basically the viscosity. Okay, so because of this eta, the particle basically moves, the particles face the viscosity, so it basically gets a frictional motion. Okay, so basically the energy of the particles dissipates because of the friction, right, of the or because of the viscosity eta. So because so since this fluctuation, that is the motion of the random motion of the particles, and eta, that is the viscosity, this basically characterize how the energy will be dissipated from the particle. Okay, so this fluctuation and this dissipations are related by this relation, so that's why this relation is basically known as the fluctuation dissipation relation. Okay, fluctuation dissipation relation, this is a very important relation that is derived by Einstein. Okay, this is known as the fluctuation dissipation relation. Okay, yeah. Now there is a treatment that is known as the Langevin treatment. Okay, so what Langevin did, or Langeva, whatever you way you can pronounce it, equation. So what Langevin does is that he basically uh, so since this particle moves, these particles face collision, these particles have random motions. Okay, so to consider all of these things in a singular, like in a singular place, he basically given or proposed the equation of motion for these Brownian particles. Okay, this equation of motion is basically known as the Brownian motions or Langevin equation of motion. Okay, so so because of that, he uses an approach that is known as the stochastic approach. Okay, where so these particles are basically, so if you consider a single Brownian particle, it it faces two kinds of motion. Okay, so this is, let's suppose, F total. The motion of the particles consists two kind of motion, right? So this particle moves because of the thermal fluctuation. There is a thermal motion, or you can say random motion, that is acting onto the particle, right? So that we are writing as if random because of that it can move randomly in different direction, right? So total force is F random plus, since these particles are in a solvent, like in a liquid medium or in a fluid medium, so because of that it will face a viscous force also, right, in opposite direction. So there is also a viscous force if the direction would be opposite. That's why I'm giving this vector direction. So this is viscous. So basically, if the particle mass is m, so m dv dt is basically F random plus F viscous. Okay, so this is kind of, this type of equation of motion is known as Langevin equations. Okay, and using this equation, like Langevin equation of motion approach also, if you calculate, like if you do the integration and all, if you calculate the mean square displacement, okay, like from this equation of motion, uh, by using this Langevin approach also, you can also show this delta, this r square, that is the msd, basically equal to kbt by 3 pi eta r into tau, the same expression that we got from the Einstein approach also. So in that way the Langevin approach and Einstein approach are both consistent with each other. Okay, so yeah, you can ask any question.
Yeah, I have a question here that you are saying it is stochastic approach because of the F random.
Yeah.
But if the F random is random, then how can we get like a fixed expression at the end?
Actually, in general, what happens? This random force, although these are not like covered during the course, but this random force has a has a expression. Okay, it's related to the temperature of the system. Okay, so this random force is proportional to the temperature. There is a functional form. Okay, which has basically derived from some mean field theory. Okay, so if you basically substitute here into the equation, if you, and after that if you do the integration both the side, after doing that you will be getting this expression of this position. Okay, like mean square displacement position. Okay.
So, like in the final form, there should be a particular like a variable or a constant which will denote the randomness of the force.
Yeah, this randomness is basically the, if you want to say how this randomness basically arise into the system, mainly because of the temperature. Okay, that we have also discussed. So this random force is the, you can say the this amplitude of random force is proportional to the temperature. Okay, so if you increase this t, this random force also get increased. Okay, and because of that the mean square displacement also get increased. Okay, that means the total motion also gets increased. Okay, similarly, if you increase the eta, that is the dissipation term, the friction term, you can see the particle will face more viscous force. The MSD also get decreased, so that means the total motion also get decreased. Okay.
Okay, okay.
Yeah. Okay. So this is a like, so Langevin use a mean field theory where the random force is basically, he has shown that the random force is basically proportional to temperature. There is a specific relations. Okay. So it's like this. So the correlation of the random force at different time, let's suppose t and t prime, where t is some later time from t prime, this correlation is related by this kind of kbt by delta t minus t prime. Okay, this is kind of a correlation of this random force. Okay, now if you substitute this thing here, okay, and doing some like this called this, what is this called, this stochastic algebra. Okay, and all of this thing, and after doing that you will be getting this expression of MSD. Okay, so this is very, like, this is the things that you will be facing in higher studies. Okay, so now
Okay.
yeah, yeah, so now is the last thing, that is the sedimentation. Okay, so sedimentation is like, yeah, so Let's suppose a water beaker is there. uh, in water beaker, if you mix some Brownian particles, okay, sedimentation is nothing but just like, because of the, if the particle size is very high, like relatively high, in that case, because of the gravity mg that is faced by each of the Brownian particle, the particles try to accumulate it into the down portion of the beaker, right? So this is called basically the sedimentation. Now in case of the Brownian particle, how this particle density, okay, the density of the how, because of the sedimentation, how this density of the particle, let's suppose is a z direction, how this density of the Brownian particle basically changes with the distance, that expression is basically can be derivable. Okay, so for that, what you have to calculate, you have to take a certain portion of the fluid, there's a pressure difference, atmospheric pressure difference, P plus dP and P. If you like balance that pressure difference with the gravitational pull that is faced by this thing, the small portion of the small fraction portion of the fluid system, or you can say in the beaker, if you basically balance out the force, dz equal to 0, from here you will be getting the expression of the pressure, that is basically given by pressure equal to P naught equal to the power mgz by RT. Now if you compare it, now if you basically substitute the expression of the uh, from kinetic theory, if you know the expression of the pressure was given by 1 by 3 mn c bar square. Now if you substitute this thing here, from this expression you'll be getting the density of the particles as a function of the distance, that is given by mgz by RT. Okay, where at z equal to z naught, z equal to 0, the particle density is n equal to n0. Okay, this is the initial condition. Now since the particles are submerged into the fluid, we know that there is a buoyancy force that will be acting onto the particle. Okay, so that force we know, so because of that force the effective mass of the particle will be different, right? So we know, let's suppose rho is the density, the particle, like the density of this particular one particle. Okay, and particle density, and rho prime, let's suppose a fluid density. In that case, we know if the particle is, let's suppose submerged into a fluid, so the buoyancy force we know is basically is, if it's a spherical particle, then in that case the force would be F into 4 by 3, if the radius of the particle is, let's suppose r, or capital R, 4 pi r cube into rho prime, right? So now the effective mass of the particle, that means m effective would be the normal mass of the particle, that is 4 by 3 r cube into rho, minus the mass that is lost because of the upward buoyancy force, right? That is 4 by 3 pi r cube rho prime. Okay, this is only when the particle is submerged inside the fluid. Okay, so m effective is basically 4 by 3 pi rho minus rho prime into r cube. Now if you substitute this thing into this equation 3, in that case from 3 you'll be getting an expression of this n as n equal to n naught exponential minus 4 pi 3 rho minus rho prime into r cube. Now if from here write it as na into g rt into z. Okay, So there are like different way, like you can write from this equation. Actually you can actually calculate what is this Avogadro number. Oh, actually, so Na is basically 3 RT 4 pi r cube. So these are two different r, right? So these are, this r is the gas constant wala r. Okay, so this is, let's write it like this, and this r is the radius. Okay, rho minus rho prime into g into z minus n naught into l n naught l. Okay, so yeah. So this way you can also calculate the uh, Avogadro number of the system. Okay, so now there is a important experiment that is done by Perrin. What he has done is basically, uh, we already discussed that what Einstein has done, right? So Einstein basically formulated these two relation, right? So where d is basically r square. R square is nothing but msd by 2 tau, and t equal to kbt 6 pi eta r. Okay, so what Perrin's experiment is that, I'm briefly telling, what he has done is that he basically these two things are completely calculated from theoretical perspective. Okay, like from solving some equation, doing some assumptions and all. So this needs further experimental validation, right? So in order to do that, what Perrin did, he basically submerged some spherical particles in some suspended water and measure this thing. This is this MSD, like we can tag one particle and how the particles basically move in the solvent water. So he basically using some camera and some other procedure, he basically calculated their mean square displacement with time. Okay, and from that you can basically equate that whole quantity with kbt by 6 pi eta r, and after doing that he actually determined this value of Avogadro number. So from here he basically calculated kb, and do you know kb is basically, and if you know the kb, you can from there you can calculate the na, right, the Avogadro number. So from this relation he basically calculated the Avogadro number. Okay, like using this expression. Okay, like using this experiment. Okay, similarly, from this sedimentation problem also, same way, doing some experiment, he has also calculated the expression of this Avogadro number. Okay, and this expression is actually accurately matched with the actual number, actual that Avogadro, what is the Avogadro number is. Because of that he got a Nobel Prize. Okay, so this I briefly like discuss how the what is basically the significance of Perrin's work. Now we will be solving some of the problems on this topic. Okay, okay. So problem number one, an experiment with colloidal particles suspended in a liquid at temperature 30 degree, okay, T equal to 30 degree centigrade, okay, shows that the MSD, that means the mean square displacement per unit time, to be 1.5 centimeter square per second. Since the mean square displacement contains square, right, so that's why the unit is given centimeter square, okay. Find the radius of the suspended particles, okay, of the particle, okay. For so some quantities are given, so Na is mentioned into the problem, 60023 into 10 to the power 23 number per mole, and the viscosity of that liquid is also given, that is 0.01 Poise. That means we can use the SI unit, right? So yeah, so we know this formula, right? So yeah, so let me write the formula here. This is the formula. So we know the diffusion constant, the R square, the MSD by 2 tau is related to kBt into 6 pi eta R, okay, where R is the radius, okay. Now from here you can write R square equal to RT by Na into 1 by 3 pi eta R into tau, okay. Now this is the important relation, this relation you have to always remember, okay. Now from here, yeah, so you have to calculate the R, so basically write this equation in terms of R, that is the radius, so R is basically RT by, yeah, so this is a different R, okay, so this R is basically the gas constant R, okay, RT by Na into 1 by 3 pi eta R square into tau, okay. So here into the problem, you know, R is the gas constant, that is 1.38 into 10 to the power minus 16. T is 303 Kelvin. Tau is unit time, that is 1. Na we know. Eta 3 pi we know, eta is 0 0.01, and R is the MSD, that is 1.5 R square. The R square is 1.5, not R, okay. Mean square displacement, okay. So just if you put everything here, so 1.38 into 10 to the power minus
Here
16.
R is not 8.314 into that.
Hmm?
It is universal gas constant, right? R.
Yeah,
So it should be 8.314 joule per mole, that unit. Because 1.38 is Boltzmann constant, right? 1.3 into 10 to the power minus
okay, okay,
23.
okay, okay, 1 second. Okay, 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 sorry. Yeah, you are saying,
Yes.
what you are saying is correct. So here, yeah, sorry, I'm writing it wrong. I misinterpreted, okay, sorry. So here R is 8.31, yeah, 8.314, and Na is 6.023 into 10 to the power 23, okay, yeah, now it's correct. So uh, yeah, so R is basically, hmm. So now just substitute the things. 8.3146.023 into 10 to the power 23. Temperature is 303. Tau is 1. 3 pi eta into 0.01 into 1.5. Now from here if you calculate the R, that is the radius, it would come as 0.29 into 10 to the power minus 12 centimeter. Okay. Yeah. Now, okay, so it's a quite easy problem. So just you have to just substitute, like carefully substitute all of the constant and all. Okay, R K eta, yeah. R is 8.314 joule. Joule Kelvin inverse mole inverse. N is gas constant. Sorry, N is the Avogadro number. Yeah, and from there you can easily calculate the radius. Okay. Yeah. So next problem. Yeah. So next problem is in an experiment of Brownian motions, the RMS displacement. Okay, so RMS. So after, so MA, if you just take a root of MSD, that gives you the RMSD. Okay, square root of MSD, that it gives you the RMSD. Okay. So the RMS displacement, that is the RMSD in horizontal direction, is given by of a spherical particle suspended in water, of a spherical particle suspended in water, is given by basically 11 micrometer over a 30-second interval. Okay, at 27 degrees centigrade. The viscosity of water is, that is given by 10 to the power minus 3 kg per meter per second. Universal gas constant R is, once here in the problem, yeah, it's written correctly. Yeah, R is given as 8.32 joule per mole inverse Kelvin inverse. Yeah, now it's given properly. Avogadro number Na is 6.023 into 10 to the power 23. Then calculate the radius of the particle. Okay, what is the R? Similar way. Okay, here the units are a bit different now. Okay, so the options are also given. 0.327. Option B is 0. It's micron. Okay, R is in micron. 218. Option C is 0.055 and option D is 0.109. Okay, so similarly, same relation, this one you have to use. Yeah, so some connection issue. Okay, so similar way, so this expression you have to use here, the expression that we previously derived. Okay, uh, so R is RT by tau into 3 pi eta n a into r square. So everything you know, delta, just you have to convert everything in particular units, right? Yeah. So here r square, so r is the RMST, that is the root mean square, okay, displacement. So r is given by micro, 1 micrometer is 10 to the power minus 6 meter, right? So 11 into 10 to the power minus 6 meter, eta is 10 to the power minus 3, T is 300 Kelvin. Just substitute all of this thing here, okay. R, like the gas constant value and everything you know, eta is 10 to the minus 3. If you do all this calculation, you will be getting R as, that is the radius R, that would be 0.109 into 10 to the power minus 6 meter. That means 0.109 micrometer or micron. Okay, 1 second. Now the third problem. So in his experiment, in his experiment means parents experiment, they are talking about. In his experiment on water suspension of gamboj at 20 degrees centigrade, Perrin observed an average of 49 particles per unit area per unit, sorry, per unit area only, per unit area in a layer, in a layer at one level, and 14 particles per unit area at a level 50 microns higher, okay, 50 microns higher. Calculate the effective mass of each particle, okay. Here the given quantities are Na, that is, we know the Avogadro numbers 0 to 3 10 to the power 23, and the gravitational constant 9.8 meter per second square. The options are given as A 4.5 into 10 to the power minus 18 kg, option B is 9.8 into 10 to the power minus 18 kg, option C is 4.74 into 10 to the power minus 17 kg, and option D is 10.32 into 10 to the power minus 18 kg. Now this experiment is nothing but the sedimentation part that we have discussed about. Okay, so uh, he wants to tell that, like in the experiment. So let's suppose this is the container water. Okay, so what Perrin observed that the suspension of particle, that means the Brownian particle, is at a particular distance, 20 degrees centigrade. The temperature is T is 20 degrees centigrade. Since the temperature plays a role, right? So in the motion of Brownian particle, so temperature is necessary. Now what's Perrin observed that uh, at a particular layer, let's suppose this layer, the particle density is 49 per unit area or per area, like this. And at a particular layer, that is 50 microns above that first layer, is there the particle density is 14 particle per unit area. So this is 14 particles per area. Okay, so this is basically we can take it as n0 and you can take it as n1 or just n, and the distance apart from this two particular level is 50 micron, right? So this is simple, right? We can just use the law of the particle density in the sedimentation problem we discussed, right? So if the particles like particles concentration would be different into the different at different height of the container, right? So that expression of the density of the particles are basically given by this particular expression that we have derived, right? That expression is n equal to n naught into e to the power minus mgz by rt, right? Where, so for our case we are considering this is the reference level where n0 is 49 particles per unit area, that we are considering as reference level, and at particular and at a distance 50 micron above that particular reference level, there the density is given by 14 particle per area, that is given by a. So that distance z here is given by 50 micron, right? So we got all of the thing, right? So we have to calculate, what we have to calculate actually, the mass of the particle, right? Yeah, the effective mass, the mass is basically the effective mass, because the particle will face this buoyancy force, right? So the mass will be get reduced, so the effective mass, that is basically the same thing is the effective mass here, that you have to calculate, right? So just rewrite the expression in terms of like the taking the m thing into the left hand side of the equation. So to do that, first take the log in both the side, from starting from this equation. If you take log both side, so this gives you one side this and another side as mgz into rt. Now from here, if you write the m in terms of the other quantities, the equation will become as rt by gz na into ln of n naught by n. This is n naught by n. Okay, now just from here, just simply substitute all the values. Okay, yeah, you know everything. In naught, z, you have to convert it into this micrometer, right? Micron, yeah. So z you have to convert into meter. Okay, so that would be 15 to 10 to the power minus 6 meter. Okay, other than is number of particles is just, this is just ln 49 by 14. Okay, and temperature T is 20 degrees centigrade, that means 270 plus 20, 290, 293, right, 293 Kelvin. Okay, and after doing all the calculation we'll be getting m equal to 10.32 into 10 to the power minus 18 kg. This would be the value of, okay. So this questions is basically directing us towards the Perrin's experiment of this water suspension experiment, where what Perrin did is that I discussed that one way is that he calculated the mean square displacement of a Brownian particle in a fluid medium. In that way he have calculated the value of the Avogadro number. In another way, what he have done is that he has done like, he has put this Brownian particles in a water suspension, in a water tank like that, and from that he done the sedimentation experiment. And as you know that from the expression of the sedimentation also, if you calculate the data, and if you compare the data, what is this, yeah, this is the expression. Yeah, if you compare the data with this expression particularly, from here itself also you will getting the expression of the Avogadro number, right? So this is the both the way actually Perrin have done the experiment, and he successfully calculated the same value of Avogadro number. Okay, so this is the second type of experiment, the sedimentation problem. The main thing you have to remember this expression. Okay, so how the particle density is changing with the distance, horizontal distance. Okay, this expression, this is the important expression here. Okay, now the question 4. Observation on Brownian motion of a spherical particle of radius given by 0.4 into 10 to the power minus 6 meter in water. Okay, at 27 degrees centigrade, and of viscosity 10 to the power minus 3 Newton second per meter square. Okay, is made. So the Brownian particle is spherical, the radius is given, the water viscosity and the temperature is given. The value of MST in 2 seconds, okay, in the 2 second interval is 1.95 into 10 to the power minus 12 meter square. Okay, so this is MSD, not RMSD, so its units will be meter square. Then compute the value of Avogadro number. So this is basically what Perrin did, right? So he, all these data he have calculated experimentally, and using the formula or the relation, the fluctuation dissipation relation, he have calculated the Avogadro number. Okay, so uh, so it's, the options are also given, although it is not needed. 9.6 into 10 to the power 23 per mole. B is 6.8 into 10 to the power 23 per mole. C is 6.3 into 10 to the power 23 per mole. Option D is 5.5 and 23 mole. You know the already the correct answer, but the main way is how you are doing the calculation. Okay, so the similar way, the starting point is similar. The relation is r square equal to RT Na into tau into 3 pi eta. This is the r, this is the radius r. Okay, now from here Na you can write it as RT into tau into 3 pi eta r into r square, right? So everything is given, right? R you know 8.314, T you know, T is given what Kelvin, 27, so 300 Kelvin, 300 Kelvin. Tau is 2 seconds. uh, R is MSD is given in which unit? MSD is meter, meter is already given. Okay, so 0.4, so R square is 0.4 into 10 to the minus 6 meter. Okay, and yeah, and eta is also required, so eta is Newton second half, so eta is also given in the same unit. Eta is also 10 to the power minus 3 here, 10 to the power minus 3. So everything is given. Sorry, MSD, yeah, sorry, I've written wrong. This is the expression of radius, 0.4, yeah, 0.4 into 10 to the power minus 6. This is the radius, and MSD was 1.95, yeah, 1.95 into 10 to the power minus 12, yeah, 10 to the power minus 12. This is a meter square. Okay, so now substitute all of this quantity here. Okay, after doing the substitution you'll be getting the expression as 6.78, a bit higher than 10 to the power minus 10 to the power 23 mole. Okay, more accurate you do the experiment, the more closer you will be getting the value of Avogadro number. Okay, now question 5. The horizontal displacements of a Brownian particle in a medium at temperature 20 degrees centigrade in 11 successive intervals of 24 seconds are 0, 5.6, minus 4.7, minus 10.8, comma 6.6, comma minus 9.8, minus 11.2, minus 4.0, 15.0, 19.1, and 16.0 micrometer. Okay, find the diffusion coefficient of the medium. Find the diffusion coefficient of the medium. Okay, so the answers are option A 2.456 into 10 to the power minus 12 meter square per second. Option B is 2.815 into 10 to the power minus 12 meter square per second. Option C is 0.755 into 10 to the power minus 12, sorry, to the power minus 12 meter square per second. Option D is 6.531 into 10 to the power minus 12 meter square per second. Okay, now here okay, so now here this is a very interesting problem. So now here we know the diffusion constant. What is the relation of the diffusion constant in terms of MSD and this time scale, the time scale on which you are doing the measurement of MSD? Okay, that is tau. So that we know from Einstein's relation is d equal to r square, that is MSD, into 2 into tau, right? This we know. Now so the value of MSD is not directly provided into the problem. Instead, what is mentioned is how the observation of MSD is happening. Okay, so as we know that MSD is nothing but what is the displacement in successive intervals. So in tau interval, the particle moves from delta x1, delta x2, delta x3. So the MSD is basically r square, or in more general way you can write it like this, r square mean. Okay, since it's a mean MSD, right? Or you can write not r square, x square you can say, as nothing but delta x1 square plus delta x2 square plus delta x3 square to delta xn square plus whole divided by n. Or in a summation fashion also you can write here there are 11 observation, right? So I equal to 1 to n delta, so delta xi square, right? Now here there is total n observation, right? So displacements, this x1 x2, these are nothing but this thing, the 5.6 4.7, these are the displacement, delta x1 delta x2 and all. Okay, now so these values are already mentioned. Okay, and the total observation here is the 11 observations. Okay, so n is basically here 11, and the interval between each observation, that is tau, that is 24 seconds. Okay, so tau is here is 24 seconds. Now if you calculate these things, okay, so x square average, that is the MSD, if you calculate this whole quantity, okay, the adding the square of each of this displacement and adding it and taking the average, if you calculate that thing, okay, so that basically gives you 1 by 11 into 0 square plus 5.6 square plus minus 4.7 square. Like this way you can do up to 16.0. So if you do all this, so these units are given in micrometer, right? So if you convert it into the meter, the whole expression would be 117.9 into 10 to the power minus 12 meter square. Okay, so this would be the value of the MSD. Now if you got MSD, you know tau. Now the substitute here into this equation of D. From there you will be getting the like the numerical value of the T. Okay, so that is 11 point, sorry, 117.9 into 10 to the power minus 12 divided by 2 into tau. Tau is 24, right? Yeah, 24. So 2 into 24. This gives you 2.456 into 10 to the power minus 12 meter square per second. So this is the expression of the diffusion constant D. Okay. Yeah, so the correct answer would be the first one. Okay. Now, yeah. So now the question number 6. So the question number 6 is, so this is a different problem. In a vertical distribution of Brownian particles, the pressure at a height z is 1 by 8 times the pressure at base. What is the ratio of number density at height z and at the base? Okay, so the options are uh, option A 1 by 16, option B 1 by 8, option C 8, and option D 16. Okay. Okay, so this is you from the structure of the problem you can easily identify it as this problem as a problem of sedimentation, right? So this is the basically, so my god, this limit is finished. Yeah, so from that structure of the problem, okay, you can easily identify it as a sedimentation problem. Okay, so pressure is like, we know that from the sedimentation problem, so let me write the expression. So P by P0, we know this, right? This the sedimentation problem. Where is it? The pressure, how the pressure is related. Uh, yeah, this one. This is the expression. Okay. So now we have to use this expression into that problem. Okay. So let me write that. So P by P0 is basically exponential minus ng z minus z naught. That is basically distance between the baseline and to the to our reference to the line that we are concerned. pressure where we want to calculate. So that is given by, so we can write this relation like this, where P is nothing by P0 by 8. So it's in the problem, it's mentioned that at a particular distance Z, the pressure is 1 by 8 times the pressure of at the base. Okay, so this is at Z, the pressure is 1 by 8 time of the pressure at the base. So P0 is the pressure at base, that is Z equal to Z0. Okay. So actually here, so from here, this relation is not needed actually. Okay, so just by P by P0, that means equal to 1 by 8, right? And we know P is simply NKT, right? So in that way, P we can write NKT, P0 we can write N0 KT, where N and N0 are basically number density. That is in the problem we have to calculate, right? Second. Yeah, we have to calculate the number density. Okay, so we just need this equation only. Okay, yeah. So P by P0 is nothing by N by N0 by 1 by 8. So that means the number density also varies by 1 by 8 relation. Okay. Next are some problems. Next are some MCQ problems that is not directly, you can say, numerical problems. In order to solve those problems, basically you have to study or write that lecture series where Sir has described like how about parents experiment. Okay, so that thing you have to watch properly in order to solve this, like in order to answer these questions. Okay, so like the first question is, seventh question is, in parents work in order to study Brownian particles. What the options are, like option A, the photograph of the particles movement were captured periodically. There are several options like these are given. Option B is the real-time particle trajectory were drawn by hand. The real-time trajectory drawn by hand. Option C is particle positions were drawn by hand at a given time interval. Positions drawn by hand given interval. And option D is particles numbers calculated. So capturing particles number calculated from photographs. So these are like, in order to solve this question you have to know how this experiment has been done. So the uh, correct answer is option C actually. Yeah, so in that time, since there is not lot of advanced machines are not invented at that time, so because of that, particle, like for a given interval, as you know, in order to calculate the MSD, so particle positions are drawn in a particular interval by hand. Okay, and from that he have calculated the MSD and the other statistical properties. Similarly, there are other questions also. like shen
Nowadays, if this experiment is repeated, then we will use a high-speed camera, right?
high speed camera also you can using microscope, very high power microscope, you can tag one particle. Okay, using some spectroscopy technique you can easily one tag one particle, and using computer you can basically calculate by using spectroscopy, like which trajectory, how many displacement the particles have made. All of these things you can calculate. Okay, you don't have to
Oh,
use your hand. Okay, yeah. Question similarly, there is another question: the ratio of Avogadro number Na as measured by Perrin is Na Perrin. So they Perrin and modern day accepted value, that is abbreviated as Na modern. Okay, modern is the ratio is basically Na Perrin by Na modern. The options are option A greater than 1, option B less than 1, option C equal to 1, definitely not is not should be equal to 1, and option D much less than 1. Okay, so here the correct option is option A actually. Okay, so whatever Perrin have measured, since there are some technological limitation, so because of that the values slightly overshoot from the actual value. Okay, so the options are equal greater than 1. Okay, okay, so these are the some of the problems that we have discussed. Okay, so if you have any questions you can ask, otherwise I will stop the class. Okay.
no question, sir. Thank you so much.
Okay.